So good afternoon to everybody. It's my great pleasure and honor to welcome all of you to this thematic session on quantum mechanics and spectral theory, which is co-organized by Svetlana Zhitomyskaya, who is following us online, and myself. And as I've been already said at the previous thematic session, we had to select the contributed talks among several dozens of potentially very interesting proposals, but we could accept only 10 of them. So the other proposals have become a poster, and so I warmly encourage all of you to give a look to the posters, which are available either here in the lobby or online through the conference platform. Okay, also, wanted to say that people who are connected online can ask questions through the conference platform in the question and answer sections. But this ends exactly when the session is supposed to be concluded. So if you have a last-minute question, just ask you through the forum, which is still active for all the time. So the next speaker of today is Johannes Kellendonk from the Institut Camille Jordan at Université de Lyon. And, let me show you the medal of the ICMP.
Do you hear me?
Professor Kellendonk will talk about diffraction and topological invariants for aperiodic systems.
Yeah, let me thank you for the invitation to present a talk here. And it's not only a very great honor for me, but I also have the advantage of not wearing my mask. So I can speak without mask. So I would like to tell you something about the connection between diffraction of solids and their topological invariants. And before I get into the details, let me tell you something about the context in which I'm going to describe this. The context is the context of aperiodic order theory, which is understood to be a theory which has developed from the discovery of quasi-crystals by Schechtmann and the understanding that aperiodic structures can have spectra which are pure point, can have X-ray spectra which are this thing is strange, which are pure point. So in this theory, which is sort of the theory about long-range ordered solids, I consider three main research lines. One is diffraction theory, so which is a theory of X-ray diffraction, so the theory which produces this picture you see on the right. Another one is spectral theory of Schrödinger operators, which you would use to calculate electronic spectra for quasi-crystals in a one-particle approximation, and mathematically is a very active area of research. Typical questions concern the question of the nature of the spectrum, Cantor spectrum, and so. And to this, I want to add a third line, which is a theory about topological invariants for aperiodic systems, which have been developed particularly in the context of the gap labeling, and now has found very much interest in the context of topological insulators and superconductors. So one question which has been asked already in the forms, various forms, but which I would like to comment on is how are these related? And the goal is then to give you a topological relation between the diffraction theory and the topological invariance. Now, I was very much motivated by a recent paper which also considers the question of how diffraction and electronic spectrum are related, or more precisely, how this is related to gap labeling. And this was actually based, if you wish, or motivated by an observation, a well-known observation that for crystals, if you treat perturbatively the potential, the Laplace plus the potential, then you can see that gaps open at positions of k wave vectors, which correspond exactly to the sharp peaks in the Brex spectrum. So the question is, can we do this aperiodically? How do I do this? Well, first of all, let me describe the topological information which is contained in this theory in a solid. This is based on a very simple description. I suppose I have finitely many types of atoms collected in a set S. And for each atomic type, I let LS be the set of all positions of the atoms in my space. So the space will be here Euclidean space, and I have discrete point sets for each atomic type 1. So here's a picture where you have two atomic types, A and B. One I've made blue, the other red. Now, all what I'm going to say will actually be pulled out of this set. So why is that reasonable? And why can I expect at all a relation between Brex spectrum and electronic spectrum, which is based on this set description of the solid? Well, if you look at the Brex spectrum, then you know, by definition, it's the pure point part of the diffraction spectrum of the electronic density, and the electronic density is produced by the local electronic densities at the atoms. For each atom type, I have one, and so there's a very simple structure. It can be written for each atomic type as a convolution of a Dirac comp on this set, which corresponds to this atomic type, with a density, which is a function which I can suppose to decay fast. And likewise, if I want to calculate the electronic spectrum, I'm going to use a potential which is local, so which is made out of atomic local potentials, which decay fast, and can be written as a sum of convolutions. So the structure of these two functions, rho and v, is very similar, and is essentially based on the structure of L. And such functions, which have this property, they can be described roughly as follows. For large R, if I look at the R neighborhood of my L near a point X, and I find that this R neighborhood at a point X looks close to the R neighborhood at another point Y, then the function takes a similar value on X and on Y. So this is a key concept, this pattern equivariance. It allows me to describe an algebra, the algebra of continuous pattern equivariant functions on my space. I won't give you the exact definition, but I repeat the informal definition a little bit closer. So a function from RDE, complex valued, I will call it pattern equivariant, if its value at X is close to the value of Y, provided the set L, or the collection of sets L, looks on a large neighborhood around X close to what it looks on a large neighborhood around Y. To make this a little bit more precise, the closeness of the neighborhoods would be measured in the Hausdorff distance, and the closeness of the function in the usual distance of complex numbers. Then you would have to put some epsilons, and then you have the precise definition. So this gives me an algebra of functions. It's closed under products. And moreover, this algebra of functions, it's hard here, it's invariant under translations because I can geometrically translate my solid in space. And so this translation action induces a continuous translation action, which they call alpha, on the algebra. So I get not only an algebra from my set L, I get also a group action. And if you take the Gelfand spectrum of this algebra, then you get a topological space. And the description I give here, I should say, is the Gelfand dual description of the description of Jean Bélissard when he described hulls of aperiodic solids. But you don't have to come from spaces and hulls. You can really define it directly on the algebra. So I have this algebra of pattern equivariant functions with a translation action. This allows me to produce in a functorial way a bigger algebra. It's the cross product algebra of my original algebra with respect to this action. This is physically very significant because you can see that the elements of this algebra, they can be approximated by operators which have continuous integral kernels, a, x, y, such that if I keep the difference y minus x fixed and let x vary, I'm pattern equivariant. So it's very manageable, and it can be seen as the C-star observable algebra of this problem, because these pattern equivariant functions hosts the potentials, hosts functions of positions which can be seen by electrons in solids, and the other copy in the cross product of RD would give me the momenta in forms of regularized derivations. Now, the topology is completely encoded in this algebra. And how is it encoded? It's encoded by the K-theory. So I should tell you a quick definition of K-theory. Let's start with invertible self-adjoint matrices with entries in A. The matrix size n, I want to be able to vary, and so I include the n cross n matrices into the n plus 1 cross n cross 1 matrices by this operation of just adding diagonally a 1. This way, I can take the union over all matrix algebras and put them together. I divide out homotopy with respect to the norm topology, and then I get a semigroup. And the semigroup law is just very simple. Take the sum of two classes, two homotopy classes of elements, and that take representatives, their direct sum. It will be again an element where the matrix size has augmented, and now I take the homotopy class of that. So that's an addition, a semigroup operation, which is commutative, and it's actually a commutative monoid. And the K0 group of the algebra is just the Grothendieck construction of this monoid, meaning that I take relative classes. That's K0. And K1 is the same thing, except that I drop the self-adjointness constraint. And if I drop the self-adjointness constraint, then it turns out that this, what was before only a monoid, is already a group. And so the Grothendieck functor doesn't give me anything new. So these are the topological invariants I'm talking about, which are associated to my solid. And I just wanted to remind you that they are now connected to topological phases, because if you consider a self-adjoint invertible operator, then you can see this as a Hamiltonian, because it's self-adjoint, which has a gap at 0, meaning that if I put the Fermi energy at 0, I have an insulator. And in physics, you like to put insulators on top of each other and connect them, so a stacking operation. And this stacking operation can be interpreted as taking elements not in the algebra, but in the matrices with entries in the algebra. And then you can formulate what is a topological space, what is a topological phase. in a sort of extended way by saying that two such gapped Hamiltonians represent the same phase, or the same if they are in the same K0 class, which means that after stacking with trivial or anti-trivial insulators, they can be deformed into each other without closing the gap. K0 though classifies topological insulators without symmetry, and K1 classifies topological phases with sublattice or chiral symmetry. Now, something which I will use, which is sort of the essential property for me of K-theory, is that K-theory has a Bott periodicity. I described K0, I described K1. I don't have to describe K2, because K2 will be isomorphic to K0. And this is based on two things. First of all, there is an alternative or an equivalent or an isomorphic description of K1, namely as the K0 group of the suspension algebra. And then the Bott map is a map which gives me an isomorphic between the K-theory of the double suspension algebra and the K-theory of the algebra. So I see that Ki plus 2 is always isomorphic to Ki. Now, in an equivalent way, I mean, Bott periodicity was sort of the first important result of K-theory, but later Kohn derived an equivalent formulation of Bott periodicity, which doesn't involve suspension, but it involves cross products. So if I have the cross product of an algebra with an R action, then Kohn proved, and that's the Kohn-Thom isomorphism, that the K-theory of the cross product is isomorphic to the K-theory of the algebra with a degree shift by 1. And since I was already talking about RD actions and their cross products, I will use that. I should maybe also mention that this is also related to the boundary map, which you find in the boundary correspondence. Now, I have abstract topological invariants. I have associated two groups to my solid, because I have associated a C-star algebra to my solid, and the construction I just described give me the groups. But they are abstract, and we want also to have numerical invariants which are numbers which can tell apart different topological phases or different classes, different elements in the K-groups. And this is something which you have seen quite a lot lately, I suppose. It's given by Chern characters, which define linear functionals on the K-groups. And for that, I need traces. And here in particular, I use the trace per unit volume and derivations. And the derivations which I have at end here, they come from this action on the algebra. I think I forgot to mention this explicitly, that I have the dual action of the group on the cross product algebra. And whenever I have a group action, I can take its infinitesimal form that gives me derivations. They will be used to construct Chern numbers. And you have seen them certainly because they also come in form of the commutator with the position operator. Now, once you have these ingredients, a trace and derivations, then you have a formula which gives you the Chern character. So this formula involves the trace per unit volume, involves the spectrally flattened form of the Hamiltonian. So I shrink the positive spectral part to 1 and the negative spectral part to -1. And the derivations and the brackets, which I denoted here, mean that I have to antisymmetrize with respect to these indices. So I have talked about the topological invariants. I told you that they are connected to topological phases. Now let me say a little bit about the Brex spectrum. The Brex spectrum actually is constructed from the electronic density, and the tool for doing so is similar as the tool for the trace per unit volume. It's sort of a convolution construction. Once I have constructed this sort of autocorrelation, I can take its Fourier transform, and I get what's called the diffraction measure. It's a measure on K-space, so I denoted R hat D. Then I can take this measure, I can decompose it into its pure point, into its continuous part, and by definition, the Brex spectrum is the support of the pure point part. So I can write the pure point part as a countable sum of Dirac measures of Dirac point masses. And the most important part of this description is that if I take the indicator's function on a point, so on a singleton set, then it corresponds to a non-zero class in the L2 space with respect to the pure point part of the diffraction measure, if and only if it belongs to the Brex spectrum. Right? So that's the characterization of the Brex spectrum. I believe that one of the fundamental theorems in diffraction theory is this theorem which is based on Dworkin's argument, which now connects the Brex spectrum to plane waves. To formulate that theorem, let me consider a Hilbert space which I obtain as the GNS representation of my algebra of pattern equivariant functions with the trace per unit volume. That's a Hilbert space. And now I can define, using diffraction, a map which is defined first on Schwarz space of K space, and goes into pattern equivariant functions. If I take a function whose Fourier transform is in Schwarz space, I undo this Fourier transform. That's what spectral analysis does. And then I convolute with the density. And that gives me a map, theta rho, between the L2 space over K space and the L2 space over position space. Now, what is important is that this map is an isometry. And if it happens that the image of the class of the function on a singleton is a continuous has a continuous representative, then it makes sense to evaluate this image on a point x, and then you calculate that you get a plane wave. So what we get is we get plane waves for Brex peak positions. And in particular, this map tells us that these plane waves belong to my algebra, and so they are pattern equivariant. This gives me the possibility now to talk about the topological content of Brex spectrum. Because if I actually come back quickly to this formula, oh, you can't come back here. No, there it is, okay. No, I don't know where I'm here. There's a clinch between the two. Okay, so if I come back to the formula for the diffraction measure, for the autocorrelation, then you see quickly that if I change the set L just a little bit, something on a set of density 0, then I won't change the diffraction. So the diffraction a priori is something which is stable under this operation. On the other hand, if I do this operation on L, then I will change drastically the algebra and the K-theory. So a priori, diffraction is not topological. So what I did here, it comes in the next slide, was to tell you, give you a way to decide what is topological in the Brex spectrum. The Brex spectrum a priori has a topological content, and this is encapsulated exactly. It's very slow, the system. It's encapsulated in this fact that the image of the indicator function on 1 has a continuous representative. And so K, I will call it a Brex, part of the topological Brex spectrum if e to the IKA is pattern equivariant. So this brings me to my main result, namely how do I connect the Brex spectrum to the K theory. I used the topological part of the Brex spectrum to do this. Well, the slide didn't arrive yet. So I can little coffee break. Okay, no, yeah. So here you see horrible. So you see E top is the topological break peak, the topological spectrum. And it's easily seen to be a subgroup of all K values. So I have a group inclusion into the K space. That's will give me one map. And the other observation is that I am topological if the plane wave is in my algebra, if it's pattern equivariant. And since waves are unitaries, they are phasors, that defines an element in K1. So I have an element in K1 of my algebra of pattern equivariant functions. And now I apply const-Tom isomorphism d times. And so I land in the observable algebra. And so this gives me a map from the topological Brex spectrum into the K theory of my algebra. And then I can also pop it out. I can also define it not only on the Brex spectrum, but also on its exterior module. And the theorem is that this operation commutes. I mean, if I measure the topological Brex values with the group inclusion map, which is induced by the inclusion, so lambda n of I. And on the other hand, I measure K-theory elements using the Chern characters. So here, in this theorem, I have an abstract identity, which is the first line. And I have a numerical identity because this commutes. Measuring invariance with Chern characters corresponds just to lambda n I. For crystals, this is an isomorphism. How much time do I still have? 3-4 minutes. OK. So then let me just give you one application of this, which is the application which corresponds to the gap labeling. The gap labeling I obtain if I set n equal to d. So I look at the same diagram here, but I look at it for n equal to d. And then it might be coming up. So there I have it, but not there. So if you look at this diagram for n equal to d, just look at the diagram here, then you see that on the right I have the Chern character within this 0. So I have the Chern character within this 0. And on the left, I have the determinant. So an element in the wedge D of my group will be d k vectors, or an antisymmetric product of d k vectors. I can write these in a matrix, and I can calculate their determinant in a certain basis. And so I have a commuting diagram for the case where the map testing K-theory corresponds simply to the trace, because the Chern character 0 is simply the trace. And then Belisar theorem was to show that actually if I do this evaluation of the K-theory, measure it with the trace, then I get exactly the gap labels, which are the values of the integrated density of states, which are negative. So the result of the right column is what's called the gap labeling group. The image of that map is the gap labeling group. And on the left, I get a result from the Brex, from the topological Brex spectrum. So this gives me an inclusion of something which comes from the Brex spectrum into the gap labeling group. For crystals and one-dimensional piezo quasi-crystals, this inclusion is an equality, but this is not always the case. And with this, I just come to my summary. I have explained to you how to derive a topological relation between the topological part of the Brex spectrum and its topological invariants. It contains, as a special case, a relation which selects out a subgroup of the gap labeling group. I can look and ask what happens if I take other values of n, and then I get something similar, except it's not for gap labels, but for winding numbers, for instance. So I could take chiral symmetry models in 2 dimensions, and then I have 2 directions for winding numbers, and form the group given by the values of these winding numbers, and see what of that comes from the Brex spectrum. And this opens up a question about how good is this? Are these maps injective? Are they surjective? Are they surjective in a virtual sense, meaning that is the image a finite index subgroup? So with this, I thank you for your attention.
Thank you very much for this inspiring talk. And let's see if there are questions from the audience. Please, Clément.
So if you apply all that to standard crystals, does this simplify to something we are familiar with in the context of topological insulators?
I didn't completely understand the question, but for crystals, these are all isomorphisms.
So it means you can read topological invariants from Brex spectrum?
Yes.
Okay.
For crystals, yeah. So for quasi-crystals, it depends. For certain values of n, you get also isomorphisms for the numerical values, but not on the level of K-theory usually. Usually the K-theory is richer. So it gives me part.
Other questions? Please, Stefan.
So I also have to try this once. Yeah, thanks a lot for the nice talk. Maybe I just missed it, but for which kind of sets L exactly do these results hold? So these are Delaune sets or?
No, anything. Uniformly discrete.
Okay.
Uniformly discrete, yeah.
And for which kind of sets do you know that these averages you presented when you said when you want to compute these Chern characters numerically, do you know in general that these averages exist or?
No, I was simply hiding this point. So it's the usual stuff. You have to go over to cluster points if the limits do not exist. So they don't have to exist, and then you have to select converging subsequences, which means effectively you throw away a little bit of information.
Okay, other questions? Then we thank Johannes again. Change the slides. The next speaker is Horia Cornean. Okay, just,
Is this working?
I think so.
Maybe
try.
not.
You don't have the first slide? a bit of...
Yeah, it's terrible. So how do I make it start? You know?
Doesn't work?
I don't know.
Yeah, yeah.
Ah, it's working. Okay.
So the next speaker of today's session is Professor Horia Cornean from University of Aalborg. Let me give you the ICMP medal.
Okay.
Yeah.
Well, thanks a lot. I think I'll just put it down. A beer would be great.
And Professor Cornean will talk about the bycatch correspondence at positive temperature.
Well, thank you very much for the invitation, and it's a big honor for me to give a talk here. I'm not a big specialist in this particular subject. Actually, I started to work on it a couple of years ago, and I learned pretty much everything from a bunch of Italians. You see them listed. Hopefully, you can read them, the names. Well, just for convenience, I will read them up. So Gianluca Panatti and Domenico Monaco, they were pretty close to me in this period. And then there is Giovanna Marcelli and Marcello Porta and Giuseppe De Nittis, who actually was the very first who mentioned to me the existence of this problem some years ago. And I want to, of course, stress some previous people who, or I mean, also existent people who did some very important work on the subject. Probably the most important remark I want to make here is that what we do in this work is to extend the previous results from 0 temperature to positive temperature. And I want to give some details about this in what follows. And I will not prove anything, it's pretty light already. I will try to explain as well as I can what the result is about and make some further comments on what are the open problems. Okay, so let me start slowly with the setting. So it's a 2-dimensional problem. Well, I'm not sure that if this works or not. Probably not. Anyway. Well, this is totally random here. So maybe I'm not. Oh, okay. So I hope that it's at least on the right spot. So this is a 2-dimensional problem. Dimension is equal to 2. And there are essentially 2 operators involved here. So there is a bulk operator, which is written in black. So there is this usual kinetic energy, where we have the momentum minus I gradient. Then there is a magnetic potential, which is periodic, so this curly A. And there is a constant magnetic part, which is B times this other A, which is linear in X. And actually, we work with the Landau gauge. So A of X is equal to, it's a vector, 2-dimensional vector, and the first component is minus X2. The other one is 0. So we can see that in this particular gauge, the operator HB, the bulk Hamiltonian, is still periodic in the X1 direction. Yeah. And for simplicity, we work with a lattice which is equal to Z2 in this case. And then there is an edge Hamiltonian. It has this extra alpha, so H alpha B is in blue. It's just the bulk Hamiltonian with the Dirichlet boundary condition at X2 equal to alpha. So you see that there is this kind of funny parameter alpha, which goes from 0 to 1. And it indicates where we put the cut in the plane. And it's enough just to consider values of alpha between 0 and 1, because otherwise the operators would be unitarily equivalent. And omega alpha is the elementary cell for a given alpha. And then if we look at the finite strip consisting of L copies of omega alpha, then the notation will be omega L comma alpha. Now, so that's a finite strip. And when, of course, L is infinity, then that will be semi-infinite. Okay, so the next important object is to choose a certain density function. So this capital F, f of x, is a function which is coincides with the Schwarz function on the spectrum of the bulk Hamiltonian. So anyway, f of x, capital F, is something which decays fast at infinity. An exponentially decaying function would be great. And you can see that one of the possible choices is to work with a Fermi-Dirac distribution. It's 1 over e to the beta times x minus mu plus 1, where beta is the inverse temperature and mu is the chemical potential. So if we want to talk about, for example, about the bulk particle density operator, then it's enough just to consider this particular function f, beta mu, acting on the bulk HB. There are some important technical facts about the integral kernel of f of HB. So f of HB is defined with the help of functional calculus. It turns out that it has a pretty nice integral kernel. So in principle, it should be x comma x prime, but this is a very smooth object, and we can put x equal to x prime. So this function f of HB of x and x is particularly nice because it's not just smooth in x, but it's also Z2 periodic. Well, I mean, I should have said from the beginning that I'm not going to treat random perturbations in this talk, but one can always add some Anderson potential. And every time you will see a trace in my talk, you should also think about averaging over the impurities if they exist. Okay. Then another important quantity, which is appeared also in Johannes' talk, is this capital B. So capital B f of little b, remember that the little b was the magnetic field, the constant magnetic field. So this is equal with kind of the local trace of f of HB. So how do we define this? Chi of omega alpha is the characteristic function of the elementary cell. And it turns out that if we multiply it with f of HB, the operator is trace class, and we can take its trace, and we can compute it as the integral of the diagonal of its integral kernel. And, well, it turns out that this is a smooth function as a function of magnetic field. And then another important quantity is this rho L alpha, in which, so remember this omega L alpha were L copies of the elementary cell. This has to be multiplied with f of H alpha b. So H alpha b is the edge Hamiltonian. This operator is again trace class. We take its trace and we divide by the number of copies of omega alpha. And so, as you see, we can also write it as a double integral, where now only x2 goes from alpha to L plus alpha, and x1 goes from 0 to 1. Okay, so you can already see the main result, and that's essentially it. So let me try to explain slowly what's going on here. The first point of the theorem in which we show that the bulk density of this capital B, f of little b, can be realized at the thermodynamic limit of rho L. Maybe it's not so surprising from the point of view of, from a technical point of view. And why is that? Because by putting an edge, and because all these operators we work are local and elliptic and so on. The influence of the edge is local. So if we go far away in the bulk, the difference between f of h alpha and f of hb will be less and less significant. So that's why it's kind of expected that rho L alpha converges to capital B, and it's not depending on the value of alpha. Well, the second identity is less trivial. So when we differentiate the bulk density capital B with respect to the magnetic field, it's still equal with the thermodynamic limit of the corresponding derivative of rho. And as I said, this is much less obvious and much less trivial to prove. And that's because the magnetic potential, so remember that the magnetic field was constant, and that generates a linearly increasing magnetic potential, and that's a singular perturbation with respect to Laplace operator, for example. So this is kind of non-trivial. And point 2 in this theorem is exactly what we call bulk boundary correspondence at positive temperature, and I will explain a little bit later why. But if you look at it, so on the left-hand side is capital B, so the derivative of the bulk density with respect to the external magnetic field can be seen as a certain limit of, so if you look on the right-hand side, it's the trace of some operator which looks very much like a velocity operator. So it's the commutator between the bulk Hamilton, the H Hamiltonian H alpha with x1. So this is the velocity operator parallel with the edge. And it's multiplied after that with the derivative of capital F, of f prime of H alpha. And then we take the trace over n copies of the elementary cell in the x2 direction. And we also have to average over the choice of the cat. So there is this extra integral with respect to alpha. So I mean, just to anticipate for a moment, the right-hand side of this identity resembles a lot with a current which runs parallel to the edge. Okay, so let me come with an important remark here. So if we choose capital F to be this particular logarithmic function, so it's -1 over beta, or let's say the temperature multiplied with logarithm and so on. And then if we differentiate this function, you get precisely the Fermi-Dirac distribution. So if I can go back to the previous formula, so now if you look at the last formula on this page, on the left is nothing but the magnetization of the system. Yeah, so capital B would be the macrocanonical potential, which depends on magnetic field, and when you differentiate that with respect to the external magnetic field, what you get is exactly the magnetization. I don't know, maybe up to a sign. I don't know. While on the right-hand side, this capital F prime would become the Fermi-Dirac distribution, so it's exactly the average current running in a direction which is parallel to the edge. Yeah, so it's magnetization on the left-hand side, bulk magnetization on the left-hand side is equal to an average current parallel to the edge, which is coming from the right-hand side. Okay, I have to say that similar results for a pure lambda operator, that means it's just constant magnetic fields in 2 dimensions, were obtained by some other people like Nicolas Macris, Philippe Martin, Joseph Poulet. That's a paper from '88. It's a very, very nice paper. And Hervé Kuntz also looked at this problem, and well, actually, what he calls the magnetic current is just a small section in a much larger paper in Journal of Statistical Physics. And I was kind of very happy to talk to all these guys many years ago, not knowing at the time that I will come back to these problems. Okay, so in those minutes I have left, I want to try to give you an idea of what the main technical steps are. So you see there are some operators there, which they turn out to be a trace class. So if you look at the first one, which I denote by I1 alpha, it looks a bit with the one in the main theorem. Oh, I pressed the wrong button. So you see that there is this the trace on the right-hand side. And actually, it turns out that if I put n equal to infinity on that formula, then I would get infinite, in the sense that it's very important that the limit is taken after taking the trace. So that operator would not be trace class in general if I put n equal to infinity, unless f prime is supported in a gap of the bulk Hamiltonian. Yeah, and this is a very important point. So you see that this operator I1 alpha, if f prime of HB would be 0, so if f prime is supported in the gap of the bulk Hamiltonian, then, okay, I mean, this commutator times f prime of H alpha would be a trace class, and the limit can be taken inside the operator. And then there is this extra identity in which you see this capital B prime is actually equal for every alpha with the difference between two traces. One can come up with a certain physical interpretation of these two terms, but I don't think I want to do that now. So anyway, maybe I should go directly to, let's say, zero temperature case. Yeah, so the formula I presented works for any capital F, and well, if we doesn't have to do anything with this particular choice which you see here. So now we assume that HB, the bulk Hamiltonian, has a gap. The chemical potential mu is inside the gap, and when the temperature becomes smaller and smaller, then this Fermi-Dirac distribution or function would converge towards an indicator function of the interval from minus infinity to mu. And we have this lemma in which we can control capital B. So it turns out that capital B is linear in capital F, which is not so surprising. And then there is another phenomenon which is interesting. I choose a function capital F0, which is equal to 1 on, let's say, the Fermi spectrum, so everything which is on the left-hand side of mu, and F0 prime is supported in the gap, but otherwise F0 is a smooth, nice function. And I can take any such function F0, and this lemma, or this proposition, which is in the second half of the page, says that if we take the temperature to 0, or beta to infinity, then the true capital B prime, well, constructed with a Fermi-Dirac distribution, converges exponentially fast to whatever value comes up by replacing F with F0. And remember that this F0 is arbitrary. If it satisfies this condition I mentioned before, then it has to be equal to 1 on the spectrum on the left of mu, and F0 prime has to be supported in the gap. And well, that means that if we take the zero temperature limit, beta tends to infinity, then we have this corollary on the bottom of the page. So again, B prime of F0 is equal to the trace of this current operator acting on, so now F is replaced by F0 prime. So on the left-hand side, we have a purely bulk quantity. On the right-hand side, we have a pure boundary quantity, which is, in this case, independent of alpha, because the left-hand side is independent of alpha. Well, I mean, just to make a connection with what everybody knows about boundary correspondence, well, it turns out that this capital B prime, if F0 has these properties I was mentioning, this is nothing but the integrated density of states of the Fermi projection, because, well, that's it. And when we differentiate this with respect to magnetic field, what it comes out is just the Chern marker of the Fermi projection, and, well, divided by 2 pi, and that's what people used to call strata formula. And there are many derivations of this formula, both in the, I mean, mostly in the let's say, tight binding models. We recently published with Domenico Monaco and Massimo Moscolari a paper, hopefully will appear this year in print. And yeah, so you see this, this nice thing which says that the Chern character or the Chern marker of the Fermi projection is equal to some boundary quantity, the thing in blue on the right-hand side. Now, I want to finish with a number of open questions. So what happens, for example, if instead of taking the cut parallel with the x1 direction, we choose to make it more complicated? And, well, in this case, you see I choose to cut with respect to the red line, and that's, it has a slope. In this case, the slope is equal to 2 divided by 5. So imagine that you have a rational slope where P and Q are co-prime, and P divided by Q is bounded by some constant. It could, so probably the most natural thing to assume is that P divided by Q converges to an irrational number, and then both these conditions would be satisfied. And then it turns out that we don't need to average over alpha anymore, provided that Q is large. So if we choose a slope which is very, very close to some irrational number, and if we take now this new elementary cell, which I denoted by omega p divided by q, instead of omega alpha before, then we still have a result which is quite similar to the previous one. The difference is that the error between capital B prime and this choice of elementary cell, so the difference between them is of order of q minus infinity. So it's, well, pretty small. And, well, okay, so what is the open question here? The open question is what happens if we start directly with a cut with an irrational slope? And we don't really know how to prove that the formula should be true. Okay, now, a second open question which I find quite challenging. Now, if we start off with this constant magnetic field to be 0, and if the original operator commutes with, well, it's a real operator, let's say, yeah, then one can prove in general that this capital B is an even function of the magnetic field. So if I differentiate it and put capital little b equal to 0, then the result is equal to 0. Now, that essentially says that the magnetization of a time reversal symmetric system at 0 magnetic field is 0. So this my fantastic formula before, it's still correct, and it consists of 0 equal to 0. Okay, so why bothering? Well, the point is that if we differentiate twice, so if you differentiate twice in this case, you get the susceptibility at 0 magnetic field. And we know that in many cases this is different from 0. I mean, that was kind of back to Landau. So the big question is there some sort of bulk boundary correspondence for the magnetic susceptibility? Can we write it maybe as, I don't know, current correlation? When I'm saying current, I'm thinking about edge current. I don't know. But anyway, it's worth investigating. Another open question is related to replacing, let's say, second order partial differential operators like Schrödinger operators with some more general elliptic pseudo-differential operators. And here there are some other issues related to how to define, well, how to put the boundary conditions and so on. So this is kind of a pretty difficult mathematical question. And then question number 4 is what happens if instead of making a cut, let's say we put a junction, and then let's say we have an asymptotic value of the magnetic field on the x2 direction, very high up, and some other different value very low down, and well, compare, see what happens in this case. And the very last open question is, of course, allowing some interaction between the particles. And I'm thinking, let's say, at least at the high temperature regime, where one can try to expand the pressure, or let's say, I mean, yeah, I didn't say that it's the pressure, the grand canonical potential with respect to the interaction between particles, and maybe investigate how the derivative with respect to magnetic field can be rewritten maybe term by term in the interaction expansion in terms of edge quantities. Okay, thank you very much, and I stop here.
Thank you, Horia, for the very nice talk. Are there questions? Please.
Thank you for your nice talk. Can you repeat which quantities depend on averaging in alpha and which not? I was a bit lost.
Well, I mean, there was, I hope I can go back. So in general, so do you see this formula here? There is a capital B prime down there. It's the trace of I1 alpha minus trace of I2 alpha. So that identity holds for each alpha. But let's say the left-hand side is independent of alpha because it's a bulk quantity, and the right-hand side is the difference of two objects. And the dependence on alpha has to cancel somehow. But it turns out that if we average over alpha, then this I2 contribution disappears. Well, I think it's an artifact of the continuous model. As I showed you here, in this case in which we choose to work with a cut along a certain rational slope, and the slope is close to an irrational number, then we don't have to average over this alpha.
So the formula with turn pi 0 is a boundary formula, or?
Okay, I mean, in this formula where you have the churn of pi 0 is equal to whatever's on the right-hand side, that's independent of alpha. So at zero temperature, the right-hand side is it's independent of alpha. So it means that you get exactly the same results irrespective of where you put the cut.
And at non-zero temperature?
At 0 temperature, yes. What did you ask?
At non-zero temperature, it depends on alpha.
It depends on alpha, yes. I mean, we cannot prove that is independent of alpha. And I guess that there is no good reason for why it should be independent of alpha. I don't know. I mean, I can tell you that for a purely Landau operator, so if it's only constant magnetic field, then there is no alpha dependence. But otherwise, we don't know.
Other questions? Okay, if not, we thank Horia and all the speakers.